Assalamu alaikum, students. So we will continue with what we have been discussing in our many lectures so far, which was basically the diode, the fabrication, the PN junction, and so on and so forth. Today we have a different topic, which is how we can use diodes in various circuit elements. And most important, as you know by now, is the rectifier circuit, in which the diode could be used to rectify the AC signal into half wave rectifier circuit as well as full wave rectifier circuit. And then we also have a very common use of the diode in terms of the basic power supply units. And finally we will be talking about the diode as a limiting or clipping circuit and diode as a switch, and so on and so forth. There are some other uses of the diodes too, which are the Zener diode, the famous LEDs, that is light emitting diodes, the photodiodes and tunnel diodes. For both these lectures I shall be using this specific reference, and I have borrowed my slides, figures, as well as circuit diagrams mostly from this lecture. That's why I have devoted a full slide to this particular reference. Now here is another very colorful slide showing you what we can wear the semiconductor PN junction diode, which is a real practical diode made of silicon or some other wide bandgap materials. I have shown you the various applications. The diode, the use of diode is most common as a junction diode, where you can use it, as I just mentioned, as a rectifier, as a Zener diode and switching diode, and then we have photodiodes and light emitting diodes. Mind you, for light emitting diode, as I just remarked a few seconds ago, we have to have a very wide bandgap material, and when we move on to the next lecture we shall be talking about the light emitting diodes in slightly greater detail. So here is a list of some very important and interesting applications in which a diode can be used. Again, I have a different type of a slide showing you where the diodes could be used, and in my today's lecture I shall be talking about mostly the rectifier and the DC power supply. Tomorrow in the next lecture we will talk about the Zener diode and LEDs. What is the purpose of having or devoting a whole lecture on the applications of the diode? Because we want to analyze the diode circuit, that how it operates and how you get the output when you give an AC alternating current or a signal to a diode. So what kind of output do you get when you apply, when you use the diode in a circuit which is known as a half wave circuit, or when you use the diode what is known as a full wave rectifier circuit. And then we also would like to discuss diodes in circuit element where it is acting as a DC power supply. Now DC power supply is a very interesting circuit in which not only we are connecting the diode with AC signal, we can have a constant output by using some components, namely transformer and filter and capacitor, about which we will be talking in detail in at a slightly later stage. So I would begin with the rectifier circuits, and I have chosen the two most common, the half wave rectifier and the full wave rectifier circuit. To begin with, to understand how the rectifier works or how diode can be used in a circuit known as rectifier circuit, let's start with the diode model, which is known as the most common or simple, which is the ideal diode model. What is an ideal diode model? We already discussed that in one of our previous lectures, that this is a diode across which we assume there is no voltage drop, or the resistance of the diode itself is almost negligible or zero, and hence there is no voltage drop across the diode, and whatever input you give to this diode, you will get an output almost equal to the input. This is the simple analogy for an ideal diode model, and that's what I have used to begin with, and then later on we will move on to a practical or a real diode, of which I have been using silicon. I have been using silicon as an example. Of course, you know by now that if you use silicon semiconductor diode, then a potential drop of 0.7 volts occurs across the diode, which is known as the barrier potential of the real or semiconductor diode. For the time being, let's concentrate on the ideal diode. So therefore, we assume that there is no voltage drop across the diode. Here is a typical illustration of the sine wave that we have chosen. The peak value is designated as Vm. This is the peak value of the input signal, input AC signal, and the peak value is Vm. The output is shown on the right of this transparency. If we are to study first the half wave rectifier circuit, the output that you get varies from 0 to pi, and the peak value is Vm. Again, I would like to mention that since we have chosen it to be the ideal diode, there is no voltage drop across it, zero voltage drop across the ideal diode, hence your output signal will be exactly equal to your input signal. The peak amplitude of the diode, of the voltage, output voltage, would be same as the input voltage. Having chosen the ideal diode model, let's move on to see how it works. When a positive half cycle, when the diode sees, or when the input signal is in the positive half cycle, our diode is said to be connected to the signal such that it is a forward bias. So when the diode is in the forward bias mode, that is when your input signal is in the positive half cycle, then the diode is forward bias, and as we mentioned before, forward bias diode conducts current or is in the on mode, and the circuit is like a short circuit. So during the positive half cycle of the input AC signal, the diode would conduct, but when the cycle moves to the negative half cycle, is in the negative half cycle, then the diode is said to be in the reverse bias, and as we already discussed, during the negative half cycle of the input signal, the reverse bias diode does not conduct, as if the ideal diode is in the off mode. So we can summarize that the diode operates during the positive half cycle, and it doesn't operate during the negative half cycle. That's the simple philosophy behind a rectifier operation. So this is what I have listed. So during the positive half cycle, you would get an output which would resemble your input positive half cycle of your input signal, and when your input signal goes to the negative half cycle, you will not get any output across your load or across your output circuit. So this is the simple manner in which the diode is rectifying, but of course you are getting only positive half cycles in your output with a blank space, if you can call it a blank space, or a missing negative half cycle. Here I have shown you on the right side of this transparency, I have shown you an illustration of a very simple circuit in which I have connected an AC line to a diode. First I have connected it to a transformer and then to a diode, and when the diode is in the forward direction, it will conduct and the current would flow, and you can get the output voltage across the load RL shown in the top of the circuit diagram. The transformer voltage, depending upon the number of turns in the secondary and primary, you would get an appropriate input. You can choose an appropriate input through the transformer for the diode, depending upon the ratio of your primary and secondary turns in the transformer. And I have shown you the transformer voltage, which the output of the transformer voltage, as I just mentioned, would depend upon the ratio of your secondary and primary turns in the transformer. And I have also shown on the diagram the pulsed DC output. I've used the word pulsed for the first time because as I just mentioned, that the output that you get across the load, shown on the top of the figure, is when the diode is conducting. That is when the diode is in the forward mode. That is when the input signal is in the positive half cycle. During the negative half cycle, the diode would be reverse biased, and therefore you would not get any output, and that has been shown by a missing negative half cycle. So our voltage across the load therefore is pulsating, which simply means consisting only of the positive cycle of the input, and the negative cycles are missing. So that's the simple way of explaining how the diode could be used in a rectifier circuit. Here is for a reverse bias, which I have already explained that the diode would not work. You would not get any output when the input signal goes into its negative half cycle. So here is the summary of how a diode, which is an ideal diode model, we have selected an ideal diode model, how this would behave. The ideal diode models, therefore, we conclude, would conduct when your input voltage Vi is positive, thereby making the diode positive or taking it into a forward bias mode. And since for an ideal diode, the resistance of the forward diode model would also be 0, therefore whatever input you give, your output will be approximately equal to your input. Since, as we mentioned before, there is no voltage drop, there is no potential barrier in the ideal diode model. Similarly, for the reverse mode, obviously in the reverse mode, the diode does not conduct during the negative half cycle of the input signal, therefore the output voltage would be 0. Now I have chosen a different model, that is a practical or a real silicon diode, not the ideal diode. For the ideal diode, there would be no voltage drop across the diode. But in a real or practical diode, let's take the example of silicon PN junction, and we know by now that in a silicon PN junction there is a voltage drop or potential barrier of 0.7 volt, and that is what I have shown on the right hand corner, and a simple diode circuit on the left hand side. Now on the right hand side, if I may explain, you would see in the blue box an ideal diode, or let me explain this way. On the left side I have shown you a real practical diode. Now come to the right side, concentrate on the blue box which I have drawn here. The ideal diode, the real semiconductor diode, can be thought of as consisting of an ideal diode, which I have marked as ideal, plus the potential drop, the barrier potential, the potential drop that takes place in a real diode, and also the diode resistance. So the left hand side, which shows a practical silicon diode, can now be considered of consisting of 3 simple components in series with each other: the ideal diode, then the barrier potential, and the diode resistance. So they are both, one is an equivalent circuit of the other. So for the half wave rectifier circuit, now I have included the barrier potential as well. What does this simply mean? This means that now the same AC signal with the same amplitude that we applied to an ideal diode would be slightly reduced by an amount equal to the diode potential barrier, because now we are talking about a practical or a real diode made up of silicon PN junction, and hence 0.7 volts would drop across this real diode, and the remaining voltage you would get as an output in a rectifying signal. So V0, that is output voltage, would now consist of V input minus 0.7. Here is an illustration of the output signal which I just talked about. So on the left side of the diagram you see the output characteristic of an ideal diode. If the voltage during the positive, as the voltage during the positive half cycle increases, so does the as the source voltage increases, so does your output voltage increases. But of course this is a linear kind of a representation. As your positive voltage increases, the source AC signal increases, so does the output voltage across the load that you are measuring or looking at the oscilloscope. I'm sure by now you know that the voltages that we apply to any given circuit are observed on the oscilloscope, because oscilloscope gives you not only the amplitude as well as the frequency of a given signal. On the right hand side you notice a blue curve as well as a black curve. The black curve corresponds to an ideal diode output, and the blue curve corresponds to a real silicon diode output, and the difference between the two obviously is your barrier potential. And input and output waveforms would be similar if your source voltage is is quite large, because compared to the barrier potential, if barrier potential becomes insignificant or very small compared to the amplitude, if you choose a very large amplitude for the input signal, then of course output signal across the load and input signal would be comparable. But if you are using small amplitudes for the input AC signal, then 0.7 would be obvious in your output signal. So here the blue diagram shows the output voltage across a real silicon diode, and the difference between the black curve and the blue curve is your barrier potential, which is 0.7 for silicon diode. Now I would like to define another term, which is the average value of the output potential that you get in a rectifier circuit. And as I mentioned before, this output voltage is measured across the load resistor that we have connected in the rectifier circuit. Here on the left side is again the same AC signal that I have chosen as an example, which varies from 0 to some peak value Vm, having a frequency shown here. I have chosen one complete cycle consisting of a positive half cycle and a negative half cycle having an amplitude Vm. So you have in the positive direction a positive Vm, and during the negative half cycle we have negative Vm amplitude. And along the y-axis I have plotted the input AC signal with a certain frequency and time period and wavelength. And on the right side I have shown you the half cycle that we get during the conduction when the diode is forward biased. Now how do we get the average value? Let's look at this full wave again. The one complete cycle varies from 0 to 2 pi, and when we integrate only, and the output on the right hand side varies from 0 to pi only. So let me repeat again. During the complete cycle from positive to negative half cycle, the waveform varies from 0 to 2 pi, but the output varies. Output is obtained only for positive half cycle, as you can see on the right hand side of this transparency. So if I integrate this output from 0 to pi, as I have done in this transparency, then after integration and for during the negative half cycle of the input, I do not get any output. So that's why I have put 0 in my bracket term. So after integration from 0 to pi, that is during the positive half cycle, the answer we get is Vm over pi. That is the average value that you get for your peak value. Output peak value has been divided by pi, and that is the method of calculating the average value of the output voltage for a negative half cycle, for a positive half, during a positive half cycle for a half wave rectifier circuit. Now I would move on a bit further. As I indicated before, that a very simple diode consisting only of a diode and a load. Let me remind you once again, the load is needed because we are dealing with an AC signal, and if you want to have the output also in an alternating form, then we have to connect it across an oscilloscope. So this varying signal, this AC signal, has to be obtained across a load, and the output that you get, even though we call it as a rectifier, but it is still changing its amplitude from 0 to some maximum value Vm, and then again 0 in a cycle from 0 to pi. So it's a pulsating DC. I call it DC, that even though the polarity is not changing, because the polarity is not changing, it is DC, but yet for the same positive polarity, it is fluctuating in its amplitude. So it's a fluctuating DC output that you get, and that is not the whole idea, because we want to have a rectified waveform, a DC waveform, which has more or less constant or some steady state value of the amplitude, not the amplitude which goes from 0 to some maximum and then again reduces to 0 is not really desirable. So what do? Then we modify or slightly enhance the construction of our simple rectifier circuit. So our rectifier circuit, to begin with, let me explain again, consisted so far of an AC signal, input AC signal, and a diode which is acting, which is the main component in a rectifier circuit. So we have an AC signal, we have a diode, and we had a load. So the simple rectifier circuit so far we had shown consisting of 3 components. But the output that we got was pulsating from 0 to some peak value Vm, and then again 0 in a cycle from 0 to pi. This is not desirable. So what do? We connect, we also include a capacitor. So such rectifier circuit is known as a smoothing rectifier circuit, because we have included a capacitor to more or less make the output constant or steady. So let's see how this circuit looks like. A small variation occurs in the DC because the capacitor discharges a small amount between the positive and negative pulses, then it recharges. This variation is called the ripple. So even though the positive half cycles are not that pulsating, but there is still some ripple because of the charging and discharging of the capacitor. The ripple appears to be a sawtooth shaped AC variation riding on the DC output. A small amount of ripple can be accepted, but sometimes the circuits or operation of certain design is so sensitive to the variation in the DC that we really have to remove even these small ripples present in the capacitor filter circuit. So here is another illustration of a circuit in which now I have shown you a capacitor and a load resistor. The sawtooth type variation that I just talked about happens because now the capacitor discharges through the load RL included in the circuit, and therefore your V output will not be constant and a ripple exists. So there is a slight ripple still, even though the capacitor has been included in this circuit, and load obviously is needed because you get the output across this load. So now a simple rectifier circuit consists of, starting from the very extreme left side of this figure, we have the input AC signal, then we have the diode, and then we have the capacitor, and we have the load across which the voltage is going to be measured or seen on the oscilloscope. How does this capacitor filter works, or in simple terms, how does the capacitor make the output in the rectifier circuit less pulsating or more smooth or more steady around some peak value? On the top I have shown you a fancy rectifier circuit which I will show you again later on. This is a bridge rectifier, so let's for the time being ignore this bridge circuit and only concentrate on the output that we get from the transformer. That is, transformer has now been included in the circuit to remove any fluctuations in your AC signal, in your input signal, so that it does not go beyond in your filter circuit. So I have shown you the transformer voltage, and let's assume that this transformer voltage is now your input to your rectifier circuit, and then I have shown you the load voltage, and so far let's say there is no capacitor included. Now you see complete, you do not see the missing negative half cycles. It's because I have the top circuit, that is the bridge circuit, the bridge rectifier circuit now has two diodes of 4 diodes, and the 2 diodes, the full wave rectifier, or the 4 diodes, the bridge circuit, now acts alternately. That is, one diode conducts when the input cycle is the positive, and the other diode conducts during negative half cycle, but it conducts because it is still with respect to the polarity anode and cathode, it is still forward bias. So by using an appropriate combination of 2 diodes so that they conduct during the positive as well as during the negative half cycles, we can obtain a voltage consisting of no missing half cycles but all positive cycles. So you get a variation, you get an output signal which has variations in amplitude, but the polarity still is constant. That is, the voltage that you get is all positive, there are no negative half cycle. So it's a kind of a DC output signal, but it is highly pulsating. So the top diagram shows you a bridge rectifier circuit. The next figure shows you the transformer output, which has been taken after the signal, initial input signal, passes through the secondary of the transformer, and then we have the output across the load. And finally, now I would like to show you how the capacitor that has been included works. So basically, the important function of the capacitor has been shown in the very bottom figure of this slide. You notice the capacitor which has been included in the circuit. So let's start again. So your capacitor, your rectifier circuit, including the capacitor, now consists of the following components. we have the input AC signal with a certain peak amplitude Vm. Then we have the transformer to eliminate any variations, any fluctuations in your input AC signal. And then we have the diode, which is the main principal component which rectifies your input signal. And then we have the capacitor, and finally we have the load across which you observe the output signal on the oscilloscope. So our circuit, rectifier circuit, whether half wave or full wave, now consists of 5 components. The important component in this circuit is the function of the capacitor itself. So that is what I want to explain. How does this capacitor works so that it gives you an output shown in the very bottom of the slide, that it resembles more or less a steady DC output rather than a pulsating output, which is shown in the third from the top, which is shown in the third figure from the top. Now, how does it work? If a large capacitor is connected across the load, this capacitor filters the pulses into a more constant DC, and hence when the diode conducts, the capacitor charges up to the peak of the sine wave and then discharges very slowly, and that is why we get a more or less steady waveform in our output circuit. In the same manner, when the sine voltage, when the negative cycle of the voltage, input voltage goes to the negative half cycle, since the capacitor is large, it forms a long time constant with the load and starts to discharge slowly, and thus during the next positive cycle, almost the recharging of the capacitor again starts, and hence during the negative cycle the capacitor is still discharging, and when the next positive half cycle comes, it starts to recharge again. So therefore the inclusion of this capacitor more or less gives you a steady output across the load. Here is another circuit diagram of an inverting half wave rectifier, and in which the combination of the diodes, 2 diodes D1 and D2, is such that one diode conducts and the other diode does not conduct, depending on the positive or negative half cycle of the input AC signal, and hence your wave is rectified. So look at the interesting combination of the 2 diodes in the upper left corner of this figure. One diode is reverse biased. Both the diodes happen to be in the reverse bias mode. So when the voltage is less than 0, that is when the diode's input voltage to the diode is negative, the diode will not conduct, but when the diode is positive, it will conduct, and thereby you get an inverting signal. Having discussed the half wave rectifier circuit, now we can very easily understand the operation of a full wave rectifier, because here what we do is we connect 2 diodes in such a manner that during the positive half cycle of the input signal, one diode conducts, and during the negative half cycle the other diode conducts. But we have to make sure that whether it is the positive half cycle from 0 to pi, or it is the negative half cycle from pi to 2 pi again, both diodes must be forward biased, so that if one is conducting, so that if diode 1 is conducting, let's say during the positive half cycle, the diode 2 must be conducting during the negative half cycle. But even during the negative half cycle, we have to keep in mind that the diode must be in the forward bias mode, and thereby we get a full wave rectifier circuit. This is the output of a full wave rectifier circuit, and again I have shown you a blue curve and a black curve. the black curve would correspond, if we assume that the diode is a simple ideal diode model, because in an ideal diode model, as we discussed for the half wave rectifier, there would be no voltage drop across the diode. The diode resistance would be approximately 0, but in a practical diode, which is a silicon semiconductor diode, the voltage drop, that is the potential barrier, has to be taken into account, which is 0.7. So your output amplitude would decrease by an amount which is potential barrier of the diode, which is 0.7. So it will reduce by an amount, decrease in amplitude by an amount equal to 0.7. Then we have the bridge circuit, the circuit I showed you earlier when I was explaining the functioning of a capacitor filter, when the capacitor was used in a rectifier circuit to give you a very smooth or more or less constant DC output. So here is that very circuit again. I have shown you a combination of two diodes. Diode D1 and D2 are forward biased. When the diode D1 and D2 are forward biased, D3 and D4 are not conducting. And when D1 and D2 are not conducting, D3 and D4 would be conducting, depending whether the cycle was such that it is making diodes forward biased, and in the negative half cycle it will be making the other two parallel diodes again forward biased. So another widely used rectifier circuit is the bridge rectifier circuit, and it uses 4 diodes. How does this circuit work and give you a complete output without any missing negative half cycle of the input? This is called a full wave rectifier, as it produces an output pulse for each half cycle of the input sine wave. On the positive half cycle of the input sine wave, diodes D1 and D2 are forward biased, so act as a closed switches appearing in series with the load. And on the negative half cycle, diode D1 and D2 are reverse biased, and diode D3 and D4 are forward biased, so current flows through the load in the same direction. This is a very simple concept to understand, that as we mentioned in one of my previous lectures, the basic principle for a diode operation is that when an anode of a diode is at a positive polarity with respect to cathode of a diode, or for real silicon diodes, that is in p-n junctions, when p side of the silicon junction is connected to a positive polarity of the battery, and n side is at a less negative potential, that is negative connected to the negative, the diode is forward biased, and hence it would conduct. But we can make the diode again in the forward direction if we connect the p side with a negative terminal and n side, that is the cathode, with a more negative. So as we mentioned in one of the lectures before, that forward biasing does not always mean that you have to connect p with a positive and n side of the p-n junction with a negative. No, we can have a forward biased p-n junction in such a way that P has to be relatively at a higher potential, and N side of the junction has to be at a relatively negative potential or lower potential. So by keeping in mind the same principle, we can design a bridge circuit or full wave circuit in such a way that if one diode is conducting during the positive half cycle, the other must be biased in such a fashion, in such a fashion that during the negative half cycle it also appears to be forward biased. So we can manipulate the biasing of the two diodes in such a way that during one cycle, which is positive, one diode is forward biased enhanced conducting, and during the other half cycle, which is negative, the second diode must be gets forward bias enhanced conducting. So both the diodes conduct during one half cycle and the other diode conducts during the second, which is negative half cycle. So both positive half cycle and the negative half cycle both give you an output which is positive, so you get a continuous that is full wave rectifier rectifying signal, and the circuit is known as full wave rectifier circuit. If there are two diodes in this particular circuit, it contains 4 diodes and it is known as a bridge rectifier circuit, but the operation is very simple, similar to a full wave diode circuit. So here I have shown you, given you a summary where the diode includes 5 components, a very simple rectifier circuit consisting of 5 components as before. The main component being the diode, then we have the capacitor which acts as a smoother for the output voltage, and then we have the load across which we draw the output voltage. In this picture, if you look at the left side, I have subtracted a voltage drop Vd on, which is the barrier potential for real silicon PN junctions. Then on the right side, on the top figure, I have shown you the bridge rectifier circuit, and at the bottom I have shown you the output that we obtain across the load for each of these half wave rectifier or full wave rectifier or bridge rectifiers. So having discussed the 3 main circuits, that is the full wave rectifier circuit, both for ideal diode and for the practical diode, the only difference would be in their amplitude, in their output amplitude. For the ideal diode model, to summarize once again, the output that you get across the load would more or less match your input signal. For a practical, that is real silicon diode, your output would be reduced by an amount 0.7 volt. Then we discussed, having discussed half wave rectifier, we talked about the full wave rectifier and the bridge circuit. Finally, then next on my list is the DC power supply, because that is another interesting and most common application of a diode after the rectifiers. In a basic DC power supply, we want to obtain from a 220 volts 50 hertz AC signal, which we have from our mains, and we want to operate some device on a DC, and the DC may be common voltages for the DC may be as small as 1 volt or 1.5 volt, and could be as large as, let's say, about 48 volts. So we have to design a circuit which gives you voltages, DC voltages of the order of their magnitude ranging from as low as 1 going up to about 50 volts. So how does a DC circuit work? I have listed about 5 different components that will be included in a circuit known as simple or basic DC power supply. Obviously, you would recall that the most common circuit for obtaining a DC output, DC signal, a DC output signal, is the rectifier circuit, and the rectifier circuit again consists of 4 basic components, namely the input signal, your diode acting as a rectifier, your load across which you measure your output signal, and then we have a filter across which you filter your ripples in the output, and then we have a regulator and a load. The rectifier converts the AC input voltage to a pulsating DC voltage. The filter here, from filter I mean the capacitor filter. The filter consisting of the capacitor eliminates the fluctuations in the rectifier voltage and produces a relatively smooth DC voltage. The regulator is a circuit that maintains a constant DC voltage, and the load is usually a circuit for which the power supply is producing the DC voltage and the load current. So these are the basic 5 components which I have shown for a simple DC power supply, and here is a colorful module for this DC power supply shown you as from left we have the AC input, and then we have the transformer, and then we have the rectifier, filter, regulator, and finally you can obtain your output across a load. I shall now discuss the functioning of this power supply, how does it operate. In a very simple circuit, rectifier circuit, we had not included any transformer. But if you want to have an undistorted or noise-free input signal, then we generally include the transformer as well. We connect the input signal first to a transformer, and then we take the transformer output, which acts as a good input signal to the remaining of your DC supply or rectifier circuit. So the AC signal first passes through a low pass filter of the form shown in the figure, and this filter eliminates the noise or any unwanted signals in our AC line supply from being transferred back into the AC line where they might interfere with other equipment. What does a transformer do, or how does a transformer work in the DC power supply circuit shown in this colorful diagram? A transformer is commonly used to step the input AC voltage level depending upon the number of turns in your primary and in your secondary. So transformer may step up the voltage to the input voltage to your other circuit, or it may step down, again as I just mentioned, depending on the number of turns in your secondary in the transformer. And for example, a transformer with a turn ratio of 10:1 would convert the I have the 110 to 60 hertz input sine wave into a 12 volt sine wave. The reference that I quoted earlier was designed for an input signal which is 120 volts and 60 hertz, but in Pakistan we use 220 volts 50 hertz input signal. But because I have used the reference which I quoted earlier, so I have kept the same figure of 120 and 60 hertz. And the ratio of the turn from primary turns to the secondary term is used, the number of turns or the ratio is used to step up or step down your signal depending upon the DC output amplitude that you want, DC output voltage that you want to get from this circuit. Finally, we have the rectifier. Well, we have studied the operation or how the rectifier works in quite a bit detail by now, so you know how the rectifier works, that we feed an AC input signal into a rectifier circuit consisting of a diode and a load, and it will give you a signal which is more or less a DC, maybe pulsating, but a constant positive polarity. Then we have the filter. Now the filter here is produces a DC output, but it is pulsating rather than constant steady value over time like that from a battery. This filter over here would in most cases be a capacitor. The most common filter, again as I have written, is a large capacitor. Let me emphasize on the word large. That filter normally refer to the component capacitor. So most of the rectifier circuits as well as most DC power supplies have capacitor component to smooth out the pulsating DC output that you get across the load. But why use a large capacitor? Well, large capacitors are used because during the positive half cycle, when they charge up, and during the negative half cycle, they are discharging slowly, and as the cycle again changes to positive, they start to recharge again. So thereby you get more or less a constant signal with slight ripple if we have a large capacitor in our DC power supply circuit. Finally, we want to regulate. So let's look back again. So we have an AC, we start from the very beginning. We have our AC input signal. We feed that, we put that AC signal we feed that to a transformer. The transformer would give you a step up or step down, will reduce the voltage or increase the voltage depending upon the ratio of the primary to secondary winding in your transformer. Then we treat the output of the transformer as an input to the remaining of the DC circuit, and then finally it is rectified, and from rectified signal we feed it to capacitor, which smoothes the pulsating DC, and now we have the regulator. What does the regulator do? The regulator is a circuit that helps to maintain a fixed or a constant output voltage, and most regulators have ICs. These are feedback control circuits that actually monitor the output voltage to detect any variations. It also, since ripples are there, ripples represent changes in the output, the regulator also compensates for these variation and produces a nearly constant output. Most electronic circuits cannot withstand the variation since they are designed to work properly with a fixed voltage. So inclusion of a regulator in the DC power supply is important, because though we are getting a smoother output after passing it through the capacitor, yet there might be some variations in the output which have to be regulated by the regulator which is put in the circuit. So we come to the end of the second application after rectifier, which was the DC design and circuit of a DC power supply. So all electronic circuits and equipment need a power supply, usually one that supplies very specific DC voltage, and as I mentioned before, DC power supplies come in a range from 1 volt to as high as 50 volts depending upon the specific purpose for which you want to use a DC power supply. Most equipment use an AC to DC power supply, and in most AC to DC supplies the 120 volt AC line is first filtered, then stepped up or stepped down to the desired voltage level, then rectified into pulsating DC, then filtered to a constant DC. A regulator holds the output to a desired level. An AC to DC converter may also be used to generate another DC voltage. So in some more advanced circuits or more complicated circuits, we can have two DC outputs from the single circuit. The two most common rectifiers are the single diode half wave rectifier and the 4 diode full wave bridge rectifier. So this brings us to the end of the power supply description, and then we would move on to the diode as a switch. Now this property of the diode, which can be utilized as a switching device, is very interesting. We have already seen that the diode conducts in one way and does not conduct in another way. What do we mean by way? when the diode or a PN junction is biased in such a way that it is forward bias, and by forward bias we mean the positive side of the diode, that is the anode, is at a relatively higher or positive potential with respect to the cathode or the N-type in the case of a silicon PN junction. Such a forward biased diode or a PN junction would allow the current to pass through as if it is acting as a short circuit and the diode is said to be in the on state. When the diode becomes reverse bias, what do we mean by reverse biasing? That is, when the anode is connected to a negative polarity of a supply, or for a silicon PN junction, when the P side of the PN junction is negatively connected, negatively biased with respect to the N side, then the diode would not conduct. In an ideal diode model, we had called such a state as a off state, or the diode is in the open. The diode is open and does not conduct, or is in the off state. So this terminology we had already defined for the case of an ideal diode model. Now for practical diodes, therefore we can utilize the same description and use the diode as a switch. Storage time or turn off transients should be small. So if the diode is to be used as a switch, then the on time, when the diode is conducting or not conducting, between these two times the time should be, the storage time of the charge should be very small. And how can we minimize that in real diodes? Well, let's discuss it in terms of the band gap of the semiconductor material. This is the band gap. This width or this distance between conduction band and valence band indicates the band gap of the semiconductor material. If the material is pure, the free electrons would be found only in the conduction band and the holes only in the valence band. But if we add impurities in the form of other atoms or some deep level defects due to the crystalline defects, they would give rise to energy levels, or they will, in simple terms, they would be sitting within the energy band gap. So an electron would find a path during its recombination process at the impurity level and then move from that impurity level to the conduction band. So if we add loss of impurity atoms, somehow deliberately add or create lots of impurity centers or steps within the band gap of a semiconductor material, it will be easier for electrons and holes to recombine, and thereby making the carrier lifetime small during the recombination process. And that is what I have written in the red lines, that if add recombination centers to reduce minority carrier lifetimes. For example, if I add 10 to the power 15 atoms of gold in silicon, it reduces the whole lifetime to 0.01 microsecond from 1 microsecond. So we see that we can reduce the carrier lifetime, and therefore the switching of the diode can be enhanced, can be made faster. Amount of the, and then we can also make another alteration in the fabrication of the diode, where the diode is to be used as a switch, that we can make, because it is acting as if we are to use a real silicon PN junction as a switch, then we have to reduce the carrier lifetime. And one of the causes that I mentioned was, if you allow electron and holes to recombine quickly, faster recombination process, that can be achieved by generating or producing recombination centers within the band gap of material. And I have illustrated an example that if we include one impurity atom per one part in a billion or one part in a million. In this example, if we have 1 million silicon atoms, and in a million silicon atoms, if I add only one gold atom, then the carrier lifetime reduces to 0.01 microsecond, from reduces to only 0.01 microsecond from 1 microsecond. 1 microsecond is the carrier lifetime, minority carrier lifetime, when there were no impurity centers. So we can have a very fast switching mode for the diode. The second method by which we can increase this switching mode is making the base very narrow, and thereby the diode would be acting as a switch. Here is the circuit diagram which you see where the diode is acting as a switch. I have shown you three different circuits. One is the three different way of showing you the same circuit. In A, I have shown you an input and output when the diode is open, and then in the middle the diode has been conducting by connecting it with an appropriate biasing, and finally I have shown you the output of this electronic switch where the diode is operating as a switch. Then we have another appropriate use of a diode, which is the diode clipper, or diode diode acting as a limiting circuit. How does it act as a limiting circuit or as a clipper? What we do here is that we make the circuit such that we connect a load RL across in parallel with the diode, and we have a resistor RS in series with the diode. So we have two resistors, one in series RS and the other in parallel RL across a diode. Now, what is the physics in this circuit? When the input signal is such that our diode under discussion is forward bias, it will have a potential drop of, depending on the value of RS and RL, the voltage drop across the diode would be 0.7 if we choose it to be a silicon PN junction, and the same value would appear across the load. The same potential drop, the diode potential drop or the potential barrier, will appear across the load RL, and the remaining value of the input voltage would appear across the resistor RS. So by choosing the appropriate load, we can have the diode conducting in such a manner that it would conduct up to 0.7 and then would clip rest of the voltage. That is, it will only start conducting after the input signal has become larger than 0.7, which is the concept of a forward biased. And the level at which the signal is clipped can be adjusted by adding a DC bias voltage in series with the diode. That is another modification to our simple clipper circuit or the limiter circuit. And the voltage that you get can be simply calculated by using the circuit which I just shown you as a potential divider. So let me take you back to the same slide which we were looking at this. So we have the voltage, the entire input signal voltage, which is VI, that is the input voltage VI, is now being divided between RS and between the voltage drop across the diode, which is the same that appears across the load. So let's move on to the mathematical evaluation now. That is, the voltage, output voltage therefore would be divided between RS and RD and the load resistor in the following manner, that it is RL, the load resistor, divided by RL plus some small resistance R. So the output voltage will be in the ratio of the load resistor and the small resistor RS. If the small resistor R is really very small compared to the value of the load resistor, or in other words, if we choose the load resistor to be a large value, which normally we do. As I mentioned once before, that load resistor normally we choose of the order of kilo ohm. So if load resistor is of the order of, let's say, 1 kilo ohm, and the small resistor is of the order of 100 ohm, then RS can be neglected compared to RL, and we would see that the output voltage would be nearly almost VI, because a very small potential drops across RS and the entire voltage appears across the diode or across the load. So this way we can design a clipper circuit. Then we have another interesting example or application of a diode, which is the Klemper circuit, and the Klemper circuit has been shown in this circuit. Another redesigning of the same circuit, where now I have connected or included a DC power supply. The DC power supply would keep the diode at a positive mode if the DC power supply happens to be greater than the negative amplitude of the input signal. And this list gives you some flavor of the circuits in which diode has been employed and various functions of the diode when used in appropriate circuits. The first one, as we see, voltage regulators. It regulates a DC supply to a fixed voltage output. Then I have switches, electronic switches, for example transistor switches. Then I have AC to DC converter, which converts an AC to a DC, and we discussed that circuit in detail. So this brings me to the end of this current lecture, in which we discussed the three important applications of a diode, most common applications of a diode, namely the rectifier circuit consisting of half wave as well as full wave, and the use of a diode in DC power supplies, the use of the diode as switches in switching circuits, and use of the diode as a clipper or limiting circuits. And finally, we would like to discuss in some more detail another use, which is the Zener diode, that is the diode in which the reverse current increases to significant or very large values at some negative values known as the breakdown values, and also how a diode can give you light. Such devices are known as light emitting diodes and photodiodes and tunneling diodes. For that we need a whole more lecture, one full lecture, another lecture, and we shall therefore postpone the discussion on Zener diode, LEDs, varactor diodes and photodiodes for next time. So I shall see you again, and I do hope that you got some idea or flavor of simple diode applications by studying diode circuits, diode rectifier circuits, diode DC power supply circuits, and diode switches. So we shall meet again. Thank you so much, and Allah Hafiz.